430,000 miles per hour. That is how fast the Parker Solar Probe races around the Sun, making it the fastest object humanity has ever built. If we could somehow aim that velocity toward the nearest star, the journey would still require roughly 7,000 years. But here is what nobody tells you. We cannot simply build a bigger rocket or wait for better technology. There is a mathematical wall blocking human expansion into the cosmos. A single equation written over a century ago proves that exponential fuel requirements create an absolute ceiling that no civilization can surpass. This barrier exists not because of engineering failures or budget limitations. It exists because of physics itself. The universe has placed a hard limit on how far biological beings can travel through space. If you enjoy journeys that challenge everything you thought you knew about our place in the universe, tap that like button and subscribe. Now, get yourself comfortable. Let's begin. In 1903, a self-taught Russian scientist published a paper that would define the boundaries of human ambition for all time. Konstantin Tsiolkovsky worked in isolation, teaching mathematics at a provincial school while dreaming of space travel. He derived a simple formula relating a rocket's speed to its fuel consumption. That formula, elegant and devastating, reveals why humanity will never conquer the stars. Tsiolkovsky spent his days explaining arithmetic to children in Kaluga. His nights belonged to calculations that no one had attempted before. He built his own wind tunnel to study aerodynamics. He designed airships decades before the Wright brothers flew. He imagined rockets carrying humans beyond Earth's atmosphere, when most scientists considered such ideas fantasy. He understood that rockets work by expelling mass in one direction to push the vehicle in the opposite direction. Newton's third law, in its purest application, but he wanted to know precisely how much propellant a rocket would need to reach specific velocities. Other scientists had considered rockets as curiosities, fireworks for celebration or weapons for war. Tsiolkovsky asked what rockets could become if scaled to cosmic ambitions. The answer he discovered haunts every space mission ever planned. The Tsiolkovsky rocket equation states that a rocket's change in velocity equals the exhaust velocity multiplied by the natural logarithm of the initial mass divided by the final mass. Written mathematically, delta V equals VE times the natural log of m0 over mf. Every spacecraft ever launched obeys this equation. Every rocket engine ever built operates within its constraints. No engineering breakthrough can escape its implications. This is not opinion or pessimism. This is physics expressing itself through mathematics. Understanding this equation requires grasping what each term means. This includes acceleration away from Earth, course corrections during flight, and deceleration at the destination. A mission to Mars requires delta V for leaving Earth orbit, for the transfer trajectory, for orbital insertion at Mars, for landing, for launching back into Mars orbit, for the return trajectory, and for Earth re-entry. Every maneuver consumes delta V from a finite budget determined before launch. Exhaust velocity measures how fast propellant leaves the rocket engine. This number depends entirely on the chemistry or physics of the propulsion system. Chemical rockets burning hydrogen and oxygen achieve exhaust velocities around 4.5 kilometers per second. Ion engines using xenon reach 30 to 50 kilometers per second. Nuclear thermal rockets might achieve 9 kilometers per second. Each propulsion technology has a characteristic exhaust velocity that cannot be significantly exceeded through engineering improvements. The exhaust velocity is fixed by physics, not by cleverness. The mass ratio compares the fully fueled spacecraft to the empty spacecraft after all propellant is consumed. A mass ratio of 10 means the rocket at launch weighs 10 times more than it will weigh after burning all its fuel. 90% of that initial mass was propellant. Only 10% remains as structure, engines, guidance systems, and payload. Higher mass ratios mean more propellant relative to everything else. The mass ratio determines what fraction of your vehicle actually goes somewhere versus what fraction gets thrown away to make the journey possible. The natural logarithm function creates the devastating mathematics that imprisons humanity. Unlike linear relationships where doubling inputs doubles outputs, logarithmic relationships grow painfully slowly. This means the inverse is also true. To achieve linear increases in delta V, you need exponential increases in mass ratio. To double your delta V, you do not need twice the fuel. You need the mass ratio squared. To triple your delta V, you need the mass ratio cubed. An ancient legend illustrates exponential growth with chilling clarity. A king offered to reward a wise man who had pleased him. The wise man asked for rice placed on a chessboard, 1 grain on the first square, 2 grains on the second, 4 on the third, 8 on the fourth, doubling each square until the board was filled. The king laughed at such a modest request and ordered it granted. The first row of 8 squares required only 255 grains, a handful of rice. The second row required over 65,000 grains, still manageable. The third row demanded nearly 17 million grains. The king grew concerned. By the 20th square, the amount exceeded 1 million grains. By the 40th square, the requirement surpassed 1 trillion grains. The 64th square alone would require more rice than has ever been harvested in human history. The total for all 64 squares exceeds 18 quintillion grains, enough to cover the entire surface of Earth several feet deep. Rocket fuel requirements follow identical mathematical behavior. The delta V for reaching low Earth orbit requires manageable mass ratios. The delta V for reaching the Moon requires mass ratios that consume the largest rocket ever built. The delta V for reaching nearby stars requires mass ratios that exceed planetary scales. The delta V for crossing significant fractions of the galaxy requires mass ratios exceeding galactic scales. The mathematics grows faster than physical reality can accommodate, exactly like grains of rice doubling on a chessboard. Let those numbers sink in. If reaching a certain velocity requires a mass ratio of 10, reaching twice that velocity requires a mass ratio of 100. 3 times that velocity demands a mass ratio of 1,000. 4 times requires 10,000. The relationship is exponential. The fuel requirements do not grow, they explode. Consider the numbers that govern chemical rockets. The most efficient chemical propellants, liquid hydrogen burned with liquid oxygen, produce exhaust velocities around 4.5 kilometers per second. This represents the ceiling of chemical rocketry. More than a century of engineering refinement has pushed combustion chamber pressures and nozzle designs toward theoretical limits. The Space Shuttle main engines achieved 4.4 kilometers per second. The RS-25 engines powering NASA's Space Launch System reach similar performance. We cannot significantly improve this number through better chemistry because we are already extracting nearly the maximum energy that hydrogen-oxygen combustion permits. Now examine what the equation demands for practical space travel. Reaching low Earth orbit requires a delta V of approximately 9.5 kilometers per second. This accounts for achieving orbital velocity, plus overcoming atmospheric drag and gravity losses during ascent. Plug these numbers into the equation. A rocket using hydrogen and oxygen needs a mass ratio of roughly 8. This means approximately 87% of the rocket's launch mass must be propellant. Only 13% remains for structure, engines, and payload. This explains why rockets look the way they do. Those towering cylinders sitting on launch pads are almost entirely fuel tanks. The actual spacecraft, the part carrying humans or satellites, perches on top like a tiny ornament on an enormous candle. Every kilogram of payload requires roughly 7 to 9 kilograms of propellant, plus the tankage to contain it. The rocket equation dictates this proportion through mathematical necessity. not engineering choice. The Saturn V rocket that carried astronauts to the moon stood 363 feet tall and weighed 6.5 million pounds at launch. Examine how that mass budget actually divided. The first stage, called the SIC, weighed 5 million pounds fully fueled. Of that, 4.7 million pounds was kerosene and liquid oxygen. The stage structure and 5 F1 engines weighed only 300,000 pounds. 94% of the first stage was propellant. The second stage, the S2, weighed over 1 million pounds. Nearly all of that was liquid hydrogen and liquid oxygen. The third stage, the S4B, added another 260,000 pounds, again mostly propellant. By the time you reach the actual spacecraft sitting on top, the Apollo command and service modules plus the lunar module, you had perhaps 150,000 pounds of useful vehicle. 150,000 pounds of spacecraft required 6.3 million pounds of rocket underneath it. The command module that returned astronauts to Earth weighed approximately 13,000 pounds. The ratio between launch mass and returning payload exceeded 500 to 1. An entire skyscraper of machinery burned to deliver a capsule smaller than a bedroom. This is not engineering inefficiency. This is the rocket equation, extracting its exponential tribute from anyone who wishes to travel beyond Earth. Consider what those moon missions actually required. The delta-V budget for a lunar landing mission totals approximately 15 kilometers per second. When you account for Earth departure, lunar orbit insertion, landing, ascent, and Earth return, chemical rockets demanded the largest vehicle humanity had ever built. 3 astronauts traveled to the moon and back while consuming more propellant than the weight of a naval destroyer. Mars expeditions demonstrate exponential growth with terrifying clarity. A round trip to Mars requires a delta-V budget of roughly 15 to 20 kilometers per second, depending on trajectory choices, whether you use aerobraking, and how long you stay on the surface. Using chemical rockets, the mass ratio climbs to approximately 20 to 30. For every kilogram you want to return from Mars, you need to launch 20 to 30 kilograms from Earth. Current Mars mission concepts from NASA and SpaceX require sending hundreds of metric tons to low Earth orbit to land, perhaps 40 metric tons on Mars. The numbers cascade exponentially. Larger missions demand larger rockets which require more fuel, which demands even larger rockets. SpaceX's Starship concept requires orbital refueling with perhaps 8 to 12 tanker flights per lunar or Mars mission. The infrastructure costs expand faster than the mission capabilities, but these challenges represent mere warm-up exercises. The exponential mass growth that makes Mars missions expensive makes interstellar missions impossible. The nearest star system, Alpha Centauri, lies 4.24 light-years away. 1 light-year equals approximately 9.5 trillion kilometers. Alpha Centauri sits roughly 40 trillion kilometers from Earth. Light itself requires more than 4 years to cross this gap. Any spacecraft traveling slower than light needs proportionally longer. Suppose humanity builds a spacecraft capable of reaching 1% of light speed. That sounds fast. 1% of 300,000 kilometers per second equals 3,000 kilometers per second. At this velocity, the journey to Alpha Centauri would take about 425 years. Generations would live and die aboard such a vessel. But the equation cares nothing for human timescales. It demands its exponential tribute, regardless of journey duration. Achieving 1% of light speed requires a delta-V of approximately 6,000 kilometers per second. This assumes you want to stop at Alpha Centauri, rather than flying past. You need 3,000 kilometers per second to accelerate, and another 3,000 to decelerate. Compare this total delta-V requirement to the 4.5 kilometers per second exhaust velocity of chemical rockets. The equation demands a mass ratio of E raised to the power of approximately 1333. This number requires explanation because human intuition cannot process it. The mathematical constant E equals approximately 2.718. Raising E to the power of 1333 produces a number with over 500 digits. For comparison, the number of atoms in the observable universe is estimated at 10 to the 80th power, a number with 81 digits. The mass ratio required for chemical rockets to reach 1% of light speed exceeds the count of atoms in existence by a factor that itself exceeds the count of atoms in existence. Read that again. To reach 1% of light speed using chemical rockets, you would need more fuel than there are atoms in the observable universe. Not more fuel than exists on Earth. Not more fuel than exists in the solar system. More fuel than the total atomic content of every star, every planet, every gas cloud, every galaxy across the entire visible cosmos. The proposition is not merely impractical. It is physically impossible. No amount of money, time, or determination can overcome the exponential barrier when numbers exceed universal limits. Some propose solving this problem by simply adding more fuel. If one fuel tank is insufficient, add 10. If 10 are inadequate, add 1,000. This intuition fails catastrophically because of how the exponential mathematics works. Additional fuel requires additional fuel to carry it. Every kilogram of propellant added at the destination end requires multiple kilograms added at the starting end. Imagine building a rocket with a mass ratio of 10. 90% propellant, 10% dry mass. This rocket achieves a certain delta V, determined by its exhaust velocity. Now, suppose you want to achieve twice the delta V. You cannot simply double the propellant. The equation demands a mass ratio of 100, 99% propellant, 1% for everything else. Structure, engines, guidance, payload all must fit within 1% of launch mass. Triple the delta V requires a mass ratio of 1000, 99.9% propellant. Quadruple requires 10,000. The dry mass fraction shrinks toward physically impossible levels. Real rockets require engines that weigh something. Real structures require materials that have mass. Real payloads cannot be infinitely miniaturized. Long before the mathematical limits are reached, physical construction limits intervene. Robert Goddard, the American rocket pioneer, understood this problem intimately. He spent decades in the 1920s and 30s building liquid-fueled rockets, proving that the technology could work. He dreamed of reaching the moon. He calculated what would be required. His notebooks contain increasingly desperate schemes to escape the exponential trap. Multi-stage designs, efficient propellants, lightweight structures. None of his designs could reach the moon. The mathematics defeated him, regardless of his engineering brilliance. He died in 1945, knowing that rockets could fly, but suspecting that the stars would forever remain beyond reach. Engineers call this the tyranny of the rocket equation. The word tyranny captures something important. A tyrant imposes restrictions through absolute power that cannot be negotiated or reasoned with. You cannot bargain with a tyrant. You cannot convince a tyrant to make exceptions. The equation exercises precisely this form of authority. You can rage against exponential mathematics. You can devise clever schemes to circumvent it. You can dream of technologies that might someday bypass it. You cannot change the fundamental relationship between velocity, exhaust speed, and mass. This relationship emerges from conservation of momentum, one of the most fundamental principles in physics. A rocket accelerates by expelling mass in one direction. The momentum gained by the rocket exactly equals the momentum carried away by the exhaust. This balance cannot be cheated. Every gram of velocity gained must be paid for with expelled propellant. The currency exchange rate is set by exhaust velocity. The total purchase price grows exponentially with the total velocity desired. Here is where the primary constraint must be stated with absolute clarity. Not energy generation, not propulsion efficiency, not material science, not funding or political will. The exponential relationship between delta V and mass ratio creates an absolute ceiling that cannot be exceeded regardless of technological advancement. This constraint governs everything that follows. Chemical rockets opened space to humanity. They carried men to the moon and robots to every planet in our solar system. Voyager spacecraft have reached interstellar space traveling at 17 kilometers per second, propelled by chemical rockets augmented by gravitational assists, but their exhaust velocity ceiling of approximately 4.5 kilometers per second restricts chemical rockets to inner solar system operations at reasonable mass ratios. Beyond Mars, beyond Jupiter, chemical rockets become ludicrously impractical. The equation reveals something profound about the universe. Physics permits travel through space but imposes severe restrictions on how far and how fast. These restrictions emerge not from engineering limitations that future technology might overcome, but from fundamental relationships between energy, mass, and motion. Conservation of momentum cannot be violated. The cosmos allows local exploration while prohibiting cosmic wandering. Human intuition fails when confronting exponential growth. Our brains evolved to track linear relationships. If one apple provides 100 calories, 2 apples provide 200. If walking 1 kilometer takes 15 minutes, walking 2 kilometers takes 30. Linear relationships dominate daily experience. Exponential relationships break this cognitive framework. They start slowly, seeming manageable, then explode beyond comprehension. Consider a thought experiment that illustrates exponential absurdity. Starting with standard paper measuring 1/10 of a millimeter, the first fold gives 2/10. By the 7th fold, the stack reaches about 1 centimeter. By the 10th fold, it reaches approximately 10 centimeters, still manageable. By the 20th fold, the stack exceeds 100 meters, taller than most buildings. By the 30th fold, it passes 1,000 kilometers, reaching beyond the International Space Station's orbit. By the 40th fold, it reaches the Moon. By the 50th fold, it approaches the Sun, reaching over 100 million kilometers. Tsiolkovsky understood these implications more than a century ago. He wrote that Earth is the cradle of humanity, but one cannot live in a cradle forever. His poetic optimism inspired generations of rocket pioneers, but embedded within his own equation lay a mathematical pessimism he may not have fully appreciated. Yes, humanity can leave the cradle. No, humanity cannot venture far beyond the nursery walls. The equation permits short walks while forbidding long journeys. The physics community has spent decades searching for alternatives to chemical propulsion. Higher exhaust velocities push back the exponential wall, providing more delta V before mass ratios become prohibitive. Ion engines achieve exhaust velocities 10 times higher than chemical rockets. Nuclear thermal rockets promise 2 to 3 times improvement. Nuclear pulse propulsion might reach 20 times better. Theoretical antimatter engines could achieve hundreds of times improvement. But none of these technologies eliminate the fundamental constraint. They merely shift where impossibility begins. Ion engines make outer solar system missions practical, but interstellar missions remain impossible. Nuclear rockets make Mars missions easier, but Alpha Centauri stays unreachable. Even antimatter propulsion, the theoretical maximum of chemical energy density, eventually confronts the exponential wall at stellar distances. This brings us back to the real limitation that governs all space travel. Every rocket that will ever fly must obey Tsiolkovsky's formula. The equation derives from conservation of momentum, which cannot be violated without violating reality itself. Every propellant that will ever burn produces a finite exhaust velocity, determined by the energy content of the reaction. Every mass ratio that climbs exponentially eventually exceeds physical possibility. The equation does not merely suggest difficulty, It mandates absolute limits. The next chapter explores advanced propulsion concepts that promise to push back the exponential wall. Ion engines, nuclear rockets, and nuclear pulse propulsion each achieve higher exhaust velocities than chemical rockets. Each technology genuinely improves humanity's reach through space. Each technology eventually confronts the same exponential barrier at larger distances. The wall moves but does not vanish. Interstellar travel demands velocities so extreme that even theoretical propulsion systems succumb to Tsiolkovsky's implacable mathematics. What humanity faces is not an engineering problem awaiting clever solutions. It is a physics problem, admitting no solution within known laws. The universe built constraints into the structure of space and time. The rocket equation translates those universal constraints into practical barriers for any civilization attempting to travel between stars. Understanding why advanced propulsion systems cannot escape these barriers requires examining each technology in detail. The mathematics remains merciless, regardless of how sophisticated the engineering becomes. Ion engines seem to offer salvation from chemical rocket limitations. Instead of burning propellant in violent combustion reactions, they accelerate ionized gases using electric fields. The principle is elegantly simple. Strip electrons from atoms to create charged particles. Use electromagnetic forces to accelerate those particles to tremendous velocities. Expel them from the spacecraft to generate thrust. The exhaust velocities reach 30 to 50 kilometers per second, nearly 10 times better than the best chemical rockets. Surely this technology unlocks the stars. The Dawn spacecraft demonstrated ion propulsion's potential across billions of kilometers. Launched in 2007, Dawn visited the asteroid Vesta, orbited it for 14 months, then departed for the dwarf planet Ceres. No chemical rocket could have accomplished both objectives. With a single spacecraft, Dawn's ion engines, each producing less thrust than the weight of a sheet of paper, accumulated velocity changes, totaling 11 kilometers per second over the mission lifetime. The spacecraft visited 2 worlds in the asteroid belt using propellant mass that chemical rockets would have exhausted reaching the first target. Ion propulsion works through patience rather than power. The thrust levels are minuscule compared to chemical rockets. Dawn's engines produced about 90 millinewtons of thrust. For comparison, the Space Shuttle main engines produced over 2 million newtons each. But ion engines can operate continuously for months or years, gradually building velocity that chemical rockets achieve in minutes of furious burning. The tortoise beats the hare. When the race spans solar system distances, the equation remains unmoved by this optimism. Higher exhaust velocity certainly helps. The mass ratio for a given delta V drops substantially when exhaust velocity increases. An ion engine with 40 km per second exhaust velocity requires a mass ratio of only about 4.5 to achieve the same delta V that demands a mass ratio of 8 from chemical rockets. This represents genuine improvement. Missions that were marginally possible become comfortable. Missions that were impossible become merely difficult. But the exponential relationship persists with mathematical certainty. For interstellar velocities, even ion engines demand impossible mass ratios. The wall simply stands farther away. It still exists. The exponential curve still climbs toward infinity. The ceiling remains absolute even if it sits higher than before. Calculate what ion propulsion requires for reaching Alpha Centauri. Assume an exhaust velocity of 40 km per second, representing advanced ion engine performance beyond current capabilities. The delta V requirement for reaching 1% of light speed and stopping at the destination remains approximately 6,000 km per second. Plug these numbers into Tsiolkovsky's equation. The mathematics demands a mass ratio of approximately e raised to the 150th power. This number contains 65 digits when written out, smaller than the mass ratios chemical rockets would require, which exceeded the number of atoms in the observable universe, but still absurdly, impossibly large. A mass ratio with 65 digits means the initial spacecraft mass would need to exceed the mass of all the planets in our solar system combined. The improvement from chemical to ion propulsion is real but insufficient by dozens of orders of magnitude. Ion engines face an additional constraint that chemical rockets avoid entirely. They require electrical power to ionize propellant and accelerate it through electromagnetic fields. This power must come from somewhere. Chemical rockets carry their energy in the propellant itself. The combustion of hydrogen and oxygen releases the energy that heats and expels the exhaust. Ion engines separate the energy source from the propellant, which enables higher exhaust velocities but creates new problems. Solar panels work magnificently near Earth. The Dawn spacecraft used solar arrays spanning nearly 20 meters to power its ion engines during the asteroid belt mission. But solar intensity drops with the square of distance from the Sun. At Jupiter's orbit, solar panels receive only 4% of the energy available at Earth's distance. At Saturn, barely 1%. At interstellar distances, solar power becomes utterly negligible. The Sun shrinks to just another star, providing no meaningful energy to spacecraft traveling between stellar systems. Nuclear reactors offer an alternative power source. Radioisotope thermoelectric generators have powered spacecraft to the outer planets for decades. Voyager, Cassini, and New Horizons all carried plutonium-238 power sources. But these generators produce only hundreds of watts, insufficient for ion propulsion at useful thrust levels. Nuclear fission reactors could produce kilowatts or megawatts, but they add substantial mass to the spacecraft. The power system mass becomes part of the dry mass fraction in the rocket equation. Remember that the equation compares fully fueled mass to empty mass. Everything that is not propellant counts as dry mass, including engines, structure, payload, and power systems. Adding a nuclear reactor to power ion engines improves exhaust velocity while simultaneously worsening the mass ratio by increasing dry mass. The gains partially cancel. For solar system missions, this trade-off favors ion propulsion. The fuel savings outweigh the power system mass penalties for journeys lasting years. For interstellar missions, the calculation becomes far less favorable. Power systems, capable of running ion engines for decades or centuries, would need to mass thousands of tons. The propellant savings diminish when the dry mass climbs so dramatically. Nuclear thermal rockets represent a different approach to improving exhaust velocity. Instead of using electricity to accelerate ions, these engines heat propellant directly by passing it through a nuclear reactor core. The propellant, typically hydrogen, flows through channels in the reactor where nuclear fission generates intense heat. Temperatures reach 2,500 degrees Celsius or higher. The superheated hydrogen expands through a nozzle, producing thrust with exhaust velocities around 9 kilometers per second. This doubles the performance of chemical rockets, where hydrogen-oxygen combustion achieves 4.5 kilometers per second. Nuclear thermal rockets achieve 9. The doubling comes from simple physics. Exhaust velocity depends on the ratio of temperature to molecular mass. Nuclear reactors can heat hydrogen to higher temperatures than chemical combustion achieves. Hydrogen's low molecular mass further improves performance compared to the heavier exhaust products of chemical reactions. The NERVA program in the 1960s demonstrated functional nuclear thermal engines. Engineers at Los Alamos and Aerojet built and tested reactors specifically designed for rocket propulsion. The engines worked. They produced the predicted thrust and exhaust velocity. Test firings accumulated hours of operation, proving the concept viable. Nuclear thermal propulsion represented proven technology by 1972. Political rather than technical obstacles ended development. Nuclear rockets required testing reactors in the open atmosphere, releasing radioactive exhaust. Environmental concerns and shifting priorities after the Apollo program concluded led to NERVA's cancellation. The technology sat dormant for decades. Recent renewed interest has prompted NASA and private companies to revisit nuclear thermal propulsion for Mars missions. But even doubling exhaust velocity provides only modest relief against exponential mathematics. For reaching 1% of light speed, nuclear thermal rockets require mass ratios exceeding e raised to the 667th power. This number contains 290 digits. Smaller than chemical requirements, but still transcending physical possibility by hundreds of orders of magnitude. Nuclear thermal propulsion enables efficient travel within the solar system. It reduces the mass required for Mars missions by substantial factors. It does not enable travel between stars. The mathematics explains why. Doubling exhaust velocity halves the exponent in the mass ratio calculation. If chemical rockets require e to the 1333rd power, nuclear thermal requires e to the 667th power. Both numbers are impossibly large. Halving an impossible exponent produces another impossible exponent. The improvement is real in percentage terms, but meaningless in practical terms. When the starting point already exceeds universal limits, nuclear pulse propulsion offered more dramatic improvements that briefly seemed to make interstellar travel feasible. Project Orion, in the 1950s and 60s, proposed propelling spacecraft using nuclear explosions. The concept sounds insane until you examine the physics. Detonate small nuclear bombs behind a massive pusher plate. The plasma from each explosion impacts the plate, transferring momentum to the spacecraft. Ride the nuclear blast waves to velocities chemical rockets could never achieve. Stanislaw Ulam and Cornelius Everett first proposed the concept at Los Alamos in 1955. Freeman Dyson joined the project and became its most famous advocate. General Atomics conducted serious engineering studies for nearly a decade. The team included some of the most brilliant physicists and engineers in America. They were not crackpots. They were serious scientists who believed they could reach the stars. Theoretical exhaust velocities for nuclear pulse propulsion reached impressive levels. Fission bombs could achieve effective exhaust velocities around 100 kilometers per second. Fusion devices might reach several hundred kilometers per second or higher. These numbers represented improvements of 20 to 100 times over chemical rockets. The exponential wall retreated dramatically. Freeman Dyson calculated that an Orion vehicle could reach approximately 3 to 5% of light speed with sufficient nuclear explosives. At 4% of light speed, the journey to Alpha Centauri would take roughly 106 years. Long but conceivably within multi-generational human planning horizons. The numbers seemed almost feasible, but examine what feasibility actually required. Reaching 5% light speed demanded a spacecraft weighing several million tons at launch. The pusher plate alone would mass thousands of tons of high-strength steel, capable of withstanding repeated nuclear explosions. The shock absorber system, connecting the plate to the payload section, would mass additional thousands of tons. The payload section, carrying passengers or cargo, contributed more mass. The propellant consisted of hundreds of thousands of nuclear bombs. Each pulse unit needed to be precisely engineered, reliably detonated, and properly directed toward the pusher plate. The total explosive yield of the propellant supply would exceed all nuclear weapons ever built by humanity. Manufacturing this quantity of bombs would require decades of dedicated industrial effort, even if political will existed. Project Orion reveals the exponential constraint through its sheer scale. Higher exhaust velocity tamed the exponential curve enough to bring mass requirements within planetary bounds rather than universal bounds. But planetary bounds still exceeded anything humanity could construct. A spacecraft larger than aircraft carriers, propelled by more nuclear weapons than exist on Earth, requiring industrial infrastructure beyond current global capacity. The project died due to nuclear test ban treaties, but even without political obstacles, construction seemed impossibly ambitious. Yet, Project Orion remains the closest humanity has come to a technically credible interstellar spacecraft design using known physics. The mathematics worked. The engineering seemed achievable, given sufficient resources. The mass requirements, while enormous, did not exceed the mass of the Moon or require more atoms than exist in the universe. For interstellar travel concepts, this counts as almost practical. All of this still fails because the mass ratio remains exponential, regardless of exhaust velocity. Orion pushed the curve downward, but could not flatten it. The relationship between delta V and mass ratio remains logarithmic. Higher exhaust velocity reduces the exponent, but does not eliminate the exponential growth. At some velocity threshold, even Orion-class spacecraft face impossible mass requirements. Consider extending Orion's reach beyond Alpha Centauri. At 5% light speed, reaching stars 10 light-years away requires 212 years. Stars 50 light-years distant require over a millennium. The payload mass fraction for such missions shrinks as journey requirements increase. Eventually, the mathematics demands spacecraft so massive that no conceivable industrial base could construct them. Fusion rockets promise even higher exhaust velocities than nuclear pulse propulsion. Controlled nuclear fusion releases enormous energy per kilogram of fuel. Where fission splits heavy atoms like uranium, fusion combines light atoms like hydrogen isotopes. The energy release per unit mass exceeds fission by factors of 3 to 4. Theoretical rocket designs using fusion achieve exhaust velocities of several hundred to several thousand kilometers per second depending on configuration. The British Interplanetary Society's Project Daedalus in the 1970s designed a fusion-powered probe using the best engineering knowledge available. The mission would reach Barnard's star, approximately 6 light-years distant, in 50 years. The probe would accelerate to 12% of light speed during a 4-year boost phase, then coast to the destination. Project Daedalus would weigh 50,000 metric tons at launch. The propellant consisted of approximately 50,000 tons of deuterium and helium-3 pellets, compressed and ignited by electron beams. 250 pellet detonations per second would propel the spacecraft. The probe was single-stage with no deceleration capability. It would fly past Barnard's star at 36,000 kilometers per second, gathering data during a brief encounter measured in hours. Return trips were never contemplated. 50,000 metric tons represents over 100 times the mass of the International Space Station. Launching this mass from Earth would require thousands of heavy-lift rocket flights or construction entirely in orbit from asteroidal materials. Project Daedalus assumed helium-3 mining from Jupiter's atmosphere, a capability humanity does not possess and has no near-term prospect of developing. The mission profile reveals the exponential constraint operating even at fusion's high exhaust velocities. 12% of light speed is impressive, but the spacecraft masses 50,000 tons to deliver a small payload on a flyby trajectory with no return. Slowing down to orbit Barnard's star would require carrying roughly twice the propellant, doubling the launch mass to 100,000 tons. Returning to Earth would require roughly quadrupling again. A round trip to Barnard's star using Daedalus-class technology would mass perhaps 400,000 tons. No matter how advanced the propulsion technology becomes, the exponential relationship between delta V and mass ratio persists with mathematical certainty. Fusion rockets achieve higher exhaust velocities than nuclear pulse. They still require mass ratios that grow exponentially with velocity demands. A fusion rocket capable of reaching Alpha Centauri at 5% light speed and stopping there needs mass ratios exceeding thousands to 1. The equation merely shifts the boundary to larger exhaust velocities without eliminating the exponential growth. Staging represents engineering's cleverest attempt to circumvent exponential mass growth. Instead of building one rocket with an enormous mass ratio, build multiple rockets stacked together. Each stage achieves a modest mass ratio, then discards empty tankage before the next stage ignites. The payload inherits velocity from all previous stages without carrying their exhausted structure. Dead weight falls away as velocity accumulates. The Saturn V used this principle magnificently. The first stage carried 5 F1 engines, burning kerosene and liquid oxygen. These engines produced 7.5 million pounds of thrust, more than any rocket stage before or since. After 2.5 minutes of flight, the first stage separated, having accelerated the vehicle to 3,000 meters per second. The second stage continued with 5 J2 engines burning hydrogen and oxygen. Higher performance propellants enabled greater efficiency for the upper stages. After 6 minutes of additional burning, the second stage contributed another 4,000 meters per second before separating. The third stage, with a single J2 engine, completed orbital insertion and sent the spacecraft toward the Moon. Each stage achieved mass ratios between 3 and 5, individually modest numbers that together accomplished the seemingly impossible. The cumulative effect reached escape velocity and beyond, while no individual stage faced unreasonable propellant fractions. Staging transformed an impossible single-stage mission into an achievable multi-stage mission. But staging offers diminishing returns as velocity requirements increase beyond Earth orbit. Each additional stage multiplies the total launch mass at the base of the stack. 2 stages with mass ratios of 5 each provide the same delta V as one stage with mass ratio 25. The mathematics works identically, but the first stage must now carry the entire second stage as its payload. If the second stage weighs 100 tons fueled, the first stage must lift that 100 tons plus its own structure and propellant. Adding a third stage compounds the pyramid effect. The third stage becomes payload for the second stage, which becomes payload for the first stage. Each stage must be sized to carry everything above it. The base stage grows dramatically with each addition. Eventually, structural limits intervene. You cannot build infinitely large rocket stages regardless of propellant availability. For interstellar missions, staging calculations become absurd exercises in exponential mathematics. Reaching 1% of light speed using chemical rockets with staging might require thousands of individual stages. Each stage carries all subsequent stages as payload. The cascade multiplies mass requirements rather than reducing them. The initial stage at the bottom of this tower would need to mass more than planets. Staging delays but does not prevent exponential mass growth from overwhelming any conceivable construction capability. The mathematics of staging can be examined precisely. If a single stage achieves delta V equal to exhaust velocity times natural log of mass ratio, then n identical stages achieve n times that delta V. To reach 6,000 kilometers per second using chemical rockets with exhaust velocity of 4.5 kilometers per second, you would need approximately 300 stages, each with a mass ratio of E approximately 2.72. 300 stages means the first stage carries as payload the combined mass of stages 2 through 300. Stage 2 carries stages 3 through 300. This pyramid structure means the initial mass exceeds the final payload by factors of e raised to the 300th power. The number has 130 digits. Staging has not solved the problem. It has merely transformed exponential propellant requirements into exponential stage count requirements. In-space refueling attempts to solve the problem by distributing propellant along the journey path. Launch fuel depots ahead of the spacecraft. Refuel en route instead of carrying everything from launch. This concept works magnificently for solar system operations, where destinations are separated by millions of kilometers rather than trillions. NASA currently plans to use in-space refueling for lunar missions. The Space Launch System will deliver Orion spacecraft to lunar orbit. Lunar landers will be refueled in orbit before descending to the surface. Propellant depots in Earth orbit and lunar orbit will enable sustainable exploration architectures. SpaceX's Mars architecture depends entirely on orbital refueling. The Starship vehicle reaches low Earth orbit partially fueled, then receives additional propellant from tanker flights. Perhaps 8 to 12 tanker launches deliver enough fuel for a single Mars-bound Starship. Interstellar distances destroy this approach through their sheer scale. Consider the logistics of in-space refueling for a journey to Alpha Centauri. You must launch fuel depots to positions between Earth and the destination. But where do you place depots in interstellar space? There are no gravitational anchors. No stable orbits exist between stars. Depots would drift unpredictably, unless equipped with their own propulsion systems consuming their own fuel. Each depot requires propellant to reach its designated position. The farther from Earth the depot needs to be placed, the more propellant it requires to get there. The depot must carry enough fuel for its own journey, plus enough to transfer to the passing spacecraft, plus enough to maintain position against solar radiation pressure and gravitational perturbations. The mass required for the depot infrastructure exceeds the mass required for direct flight. You are now launching fuel to lift fuel to provide fuel. The exponential mathematics operates on the depot system, just as it operates on the spacecraft itself. Multiple depots multiply the problem rather than dividing it. For destinations within the solar system, gravitational assists reduce delta V requirements and make refueling architectures practical. Spacecraft can swing past planets, borrowing momentum from their orbital motion. Voyager used Jupiter's gravity to reach Saturn, then Saturn's gravity to bend toward interstellar space. These assists are free delta-v gifts from orbital mechanics. Aerobraking offers another free delta-v source for planets with atmospheres. Spacecraft can shed velocity by dipping into planetary atmospheres, using air resistance instead of propellant to slow down. Mars missions routinely use aerobraking to reduce propellant requirements for orbital insertion. These options vanish completely in interstellar space. There are no planets to swing past between stars. No atmospheres exist in the void to shed velocity. No gravitational assists are available in the empty parsecs separating stellar systems. Every kilometre per second of delta V must come from onboard propellant or externally supplied energy. The universe offers no shortcuts across interstellar distances. The propulsion trap closes around every technology humanity has conceived or theorized. Chemical rockets hit exponential walls within the inner solar system. Ion engines extend practical range to the outer planets, but confront the same mathematics at interstellar scales. Nuclear thermal rockets enable efficient Mars transportation, but offer no path to the stars. Nuclear pulse propulsion approaches credibility for Alpha Centauri at costs exceeding global industrial capacity. Fusion rockets push performance envelopes while still facing exponential constraints. Each technology improves on its predecessors by genuine factors. Ion engines outperform chemical rockets by factors of 10 in exhaust velocity. Nuclear thermal doubles chemical performance. Nuclear pulse achieves factors of 20 or more. Fusion might reach factors of 50 to 100. These improvements matter enormously for solar system exploration. They reduce mission costs, enable new destinations, and expand human reach through nearby space. But interstellar distances demand improvements of thousands or millions, not tens or hundreds. The gap between what advanced propulsion achieves and what interstellar travel requires spans too many orders of magnitude. Closing that gap runs directly into the exponential mathematics of the rocket equation. Each doubling of exhaust velocity halves the exponent in mass ratio requirements. But when the starting exponent contains hundreds of digits, halving it repeatedly still leaves impossible numbers. This brings us back to the real limitation governing all proposed propulsion systems. The rocket equation contains a natural logarithm relating delta V to mass ratio and exhaust velocity. This mathematical function grows slowly in one direction and explosively in the other direction. To achieve large delta V values from modest exhaust velocities, mass ratios must be enormous. The relationship is fundamental. It derives from conservation of momentum. It cannot be negotiated, circumvented, or escaped through engineering cleverness. No propulsion technology changes this relationship. Higher exhaust velocities reduce required mass ratios for given delta-v targets. This is real and valuable progress. But they do not eliminate the exponential growth that eventually overwhelms any mission attempting stellar distances. The curve flattens but never becomes linear. The wall retreats but never vanishes. The universe permits improvements in spacecraft propulsion. Better engines produce higher exhaust velocities. Better materials enable higher mass ratios before structural failure. Better energy sources provide more power per kilogram. Better manufacturing enables lighter components. Better mission design reduces delta-v requirements through clever trajectory optimization. All of these improvements are real and valuable, but all improvements operate within Tsiolkovsky's framework. Every spacecraft that expels mass to generate thrust obeys the rocket equation. Every improvement in exhaust velocity helps, but does not fundamentally change the exponential mathematics. None escape the equation. None can escape it because the equation derives from conservation of momentum, a principle as fundamental as the existence of matter itself. Spacecraft engineers have known this for decades. The textbooks explain it clearly. The mathematics is unambiguous, yet the optimism surrounding space exploration rarely acknowledges the mathematical prison surrounding interstellar travel. Press releases celebrate incremental advances without mentioning ultimate limits. Mission planners design ever more capable vehicles for solar system exploration without discussing why similar vehicles cannot reach the stars. The public assumes that eventually, somehow, technology will solve the problem. The equation guarantees otherwise. What remains to explore are propulsion concepts that abandon traditional rocketry entirely. Perhaps beamed energy from external sources can accelerate spacecraft without requiring them to carry fuel. Perhaps exotic physics provides escape routes from conventional limitations that known physics does not offer. The next chapter examines these speculative proposals with the same mathematical rigor applied to chemical, ion, nuclear thermal, nuclear pulse, and fusion rockets. Antimatter propulsion, laser sails, generation ships, warp drives, and wormholes each promise ways around the rocket equation. Each encounters its own version of the fundamental barrier. The results offer little comfort to those dreaming of stellar empires spanning the galaxy. The propulsion trap is real. It is mathematical. It is permanent. Humanity can push against its boundaries and expand the range of the possible within the solar system. Humanity cannot escape the trap through propulsion improvements alone. The exponential mathematics of mass ratios ensures that interstellar velocities remain forever beyond reach for any rocket-propelled spacecraft, regardless of the fuel it burns or the engines it employs. Antimatter represents the ultimate fuel. When matter meets antimatter, both annihilate completely, converting 100% of rest mass into energy, according to Einstein's famous equation. Compare this efficiency to chemical rockets extracting a few millionths of a percent of mass energy. Compare it to nuclear fission releasing less than 1%. Compare it to nuclear fusion achieving perhaps 1%. Antimatter stands alone as the theoretical maximum of energy density available from known physics. The numbers appear miraculous. 1 kilogram of antimatter annihilating with 1 kilogram of ordinary matter releases approximately 180 petajoules of energy. Written out, that equals 90 quadrillion joules. This energy content exceeds 2 million metric tons of liquid hydrogen and oxygen propellant. A thimbleful of antimatter contains more energy than the largest nuclear weapons ever detonated. Surely this energy density eliminates the propulsion problem. Surely antimatter unlocks the stars. The physics of matter-antimatter annihilation produces exhaust velocities that dwarf all other propulsion concepts. When electrons meet positrons, they convert entirely to gamma rays traveling at light speed. When protons meet antiprotons, the annihilation produces pions that decay through various channels, ultimately yielding gamma rays and other particles moving at substantial fractions of light speed. Theoretical rocket designs using antimatter achieve effective exhaust velocities of 10 to 30% of light speed, depending on how efficiently the annihilation products can be directed. Tsiolkovsky's equation acknowledges antimatter's impressive performance. Mass ratios for interstellar travel drop substantially compared to chemical, nuclear, or fusion options. A spacecraft using matter-antimatter annihilation might achieve 10% of light speed with mass ratios in the hundreds, rather than the billions or trillions required by lesser technologies. The numbers transition from physically impossible to merely astronomically impractical. Consider a specific calculation. Reaching 10% of light speed with deceleration capability requires a delta V of 60,000 km per second. Using antimatter propulsion with an effective exhaust velocity of 20% of light speed, approximately 60,000 km per second, the rocket equation demands a mass ratio of E, roughly 2.72. This means the spacecraft would need to be about 63% propellant by mass. Challenging, but not impossible. The exponential wall finally seems climbable, but antimatter faces production constraints that dwarf all other propulsion challenges combined. Creating antimatter requires particle accelerators that smash protons or electrons together at tremendous energies. The collisions occasionally produce particle-antiparticle pairs. Collecting and storing the antiparticles demands sophisticated electromagnetic traps operating at temperatures near absolute zero. The entire process consumes vastly more energy than the antimatter will ever release. CERN, the European Organization for Nuclear Research, operates the world's most sophisticated particle physics complex. Their facilities include the Large Hadron Collider and numerous smaller accelerators dedicated to antimatter research. The antiproton decelerator produces antiprotons for fundamental physics experiments. The alpha and ATRAP collaborations have trapped antihydrogen atoms for extended periods. These represent humanity's most advanced antimatter capabilities. CERN produces approximately 10 nanograms of antimatter per year across all its facilities. A nanogram equals 1 billionth of a gram. At this production rate, accumulating a single gram of antimatter would require 100 million years of continuous operation. Producing 1 kilogram, the minimum useful quantity for a small interstellar probe, would take 100 billion years. The universe itself is only 13.8 billion years old. Current production rates make antimatter propulsion literally impossible on any timescale shorter than cosmic epochs. The energy economics compound this impossibility. Creating antimatter requires pumping enormous energy into particle accelerators. The efficiency of antimatter production currently stands at approximately 1 part in 10 billion. For every 10 billion joules of energy consumed by the accelerator complex, roughly 1 joule worth of antimatter results. Using this antimatter as rocket fuel means expending 10 billion joules to eventually recover 1 joule of propulsive energy. Even theoretically perfect production efficiency would not solve the problem. The minimum energy required to create a kilogram of antimatter equals the energy that kilogram would release upon annihilation, roughly 90 petajoules. This equals the annual electrical output of several large nuclear power plants. Creating the hundreds or thousands of kilograms needed for interstellar missions would consume energy equivalent to decades of global electrical production. The antimatter becomes merely a storage medium for energy that could be used more efficiently through other means. Storage presents barriers nearly as severe as production. Antimatter annihilates instantly upon contact with ordinary matter. Any containment system must prevent all physical contact between the antimatter fuel and the container walls. This requires suspending charged antiparticles in magnetic fields within perfect vacuums. The slightest failure, a single antiproton touching a single proton in the container wall, releases energy and begins a cascade that could destroy the entire fuel supply explosively. Current antimatter traps maintain antiparticles for periods measured in minutes or hours. The Alpha experiment at CERN trapped antihydrogen atoms for approximately 17 minutes before losses accumulated. Interstellar journeys lasting decades or centuries would require containment systems operating flawlessly for millions of times longer than any current technology achieves. The reliability requirements exceed anything humanity has ever engineered by factors of billions. The containment equipment itself adds mass that worsens the rocket equation. Magnetic traps require superconducting coils operating at temperatures near absolute zero. Cooling systems, power supplies, and structural supports for the magnetic containment all contribute to spacecraft dry mass. The mass of containment equipment may approach or exceed the mass of antimatter being contained. This dramatically reduces the effective energy density advantage that made antimatter attractive in the first place. All of this still fails because even theoretical antimatter rockets cannot escape exponential mass scaling entirely. The exhaust velocity of matter-antimatter annihilation products approaches but does not reach light speed. Gamma rays travel at light speed but cannot be directed efficiently as rocket exhaust. Charged pions can be magnetically directed but travel at only 94% of light speed and decay within nanoseconds. Practical designs must compromise between efficiency and directability, achieving effective exhaust velocities far below the theoretical maximum. For journeys requiring velocities above 10% of light speed or missions to stars beyond Alpha Centauri, mass ratios climb back toward impractical levels, even with antimatter. The exponential mathematics operates on lower exponents than chemical or nuclear rockets, but still operates. The wall stands farther away. It still exists. Antimatter postpones the limit rather than eliminating it. Beam-powered propulsion attempts to escape the rocket equation through a fundamentally different approach. Instead of carrying fuel, the spacecraft receives energy from external sources. Lasers or microwave emitters stationed on Earth or in solar orbit push lightweight sails to tremendous velocities. The spacecraft mass drops dramatically because it carries no propellant whatsoever. The rocket equation seems not to apply to vehicles that carry no rockets. The physics is straightforward. Photons carry momentum despite having no rest mass. Light reflecting from a surface transfers momentum to that surface. A powerful enough light source pushing against a reflective sail can accelerate a spacecraft without any onboard propellant consumption. The sail acts as a mirror, the laser acts as the engine, and the engine stays home while the spacecraft departs. Solar sails have already demonstrated this principle within the solar system. Japan's Ikaros spacecraft deployed a 14-meter sail in 2010 and achieved measurable acceleration from solar radiation pressure. The Planetary Society's LightSail 2 raised its orbit using sunlight alone. These demonstrations prove the concept works, though solar radiation provides only gentle acceleration suitable for inner solar system maneuvers. Replacing sunlight with focused laser beams dramatically increases available power. A laser array can concentrate energy that would otherwise spread across millions of square kilometers of solar illumination into a beam targeting a single sail. The acceleration scales with power density. Sufficiently powerful lasers could push sails to velocities utterly unachievable by solar radiation alone. Breakthrough Starshot exemplifies the most ambitious laser sail proposal. Announced in 2016 with funding from Russian billionaire Yuri Milner, the project proposes accelerating gram-scale probes to 20% of light speed using ground-based laser arrays. At 60,000 kilometers per second, these probes would reach Alpha Centauri in approximately 20 years. Cameras and communication lasers weighing mere grams would transmit images back to Earth. The concept eliminates onboard propellant entirely, seemingly escaping Tsiolkovsky's equation. Examine the engineering requirements carefully. Accelerating a 1-gram probe to 20% of light speed requires adding kinetic energy of approximately 1.8 terajoules. This energy must be delivered through laser illumination during the brief acceleration phase, while the probe remains close enough for the beam to focus effectively. Atmospheric absorption, beam spreading, and sail reflectivity losses mean the laser array must output substantially more than this minimum energy. Breakthrough Starshot's baseline design calls for a laser array producing approximately 100 gigawatts of power. The array would illuminate a 4-meter sail for approximately 10 minutes, accelerating the probe through tens of thousands of gravities. The beam must remain focused on a target centimeters across at distances increasing from near Earth to millions of kilometers during the acceleration phase. The pointing accuracy requirements are staggering. A beam divergence of 1 part in 10 billion is needed to maintain focus on the sail throughout acceleration. Atmospheric turbulence distorts laser beams passing through Earth's atmosphere. Adaptive optics can partially correct these distortions, but not perfectly. Placing the laser array in space avoids atmospheric problems, but requires lifting hundreds of thousands of tons of equipment into orbit, facing the rocket equation's full constraints for the construction phase. But beam-powered propulsion merely transfers exponential mass growth from spacecraft to infrastructure. The laser array itself has mass. More powerful arrays accelerate larger payloads or achieve higher velocities. But more powerful arrays require more laser emitters, more power supplies, more cooling systems, more structural support. The infrastructure mass scales with capability requirements through relationships that eventually become exponential. Consider scaling Breakthrough Starshot to human passengers. A minimal crewed spacecraft might mass 10,000 kilograms with passengers and life support. Accelerating this payload to even 1% of light speed requires 100 trillion times more energy than the gram-scale probe. The laser array would need to output approximately 10 million terawatts for the duration of acceleration. This exceeds the total solar energy reaching Earth by factors of thousands. The array size would exceed any structure humanity could construct. The sail itself faces impossible structural requirements at human payload scales. Breakthrough Starshot's gram-scale probes use sails only meters across, made from materials at the edge of theoretical strength limits. Scaling to 10,000 kilogram payloads requires either enormous sails or incredible material strengths. Sails large enough to intercept sufficient laser energy would mass thousands of tons, dominating the payload mass they are supposed to accelerate. The mass ratio problem returns through sail sizing rather than fuel requirements. Laser sails also cannot decelerate at their destination without additional infrastructure. The spacecraft arrives at Alpha Centauri, traveling at 20% of light speed with no way to slow down. Flyby missions gather data during brief encounters lasting hours. Orbital insertion or landing requires deceleration that laser sails cannot provide without a laser array at the destination. Building such an array requires sending construction equipment that faces the original propulsion problem. Sail materials face thermal limits that constrain acceleration rates. Laser illumination heats the sail material. Higher power densities enable faster acceleration but risk melting or vaporizing the sail. The optimal sail reflects nearly all incident light while absorbing almost nothing. Real materials fall short of this ideal. Breakthrough Starshot requires sail materials with reflectivity exceeding 99.9% and absorption below 1/100%. Such materials do not currently exist and may not be physically achievable. Generation ships represent a philosophically different approach to interstellar travel. Instead of fighting the rocket equation for higher velocities, accept slow travel and plan for journeys lasting centuries. Build spacecraft large enough to sustain human populations for multiple generations. Let passengers be born, live, and die aboard the vessel. Their descendants eventually arrive at the destination. The appeal is obvious. Chemical or nuclear rockets could accelerate generation ships to perhaps 1% of light speed with mass ratios in the merely difficult rather than impossible range. At 1% of light speed, Alpha Centauri lies 425 years away. Multiple generations would pass, but the mathematics appears workable. Why fight exponential growth when patience offers an alternative path? But generation ships face exponential mass growth in life support rather than propellant. They breathe roughly 550 litres of oxygen. They produce carbon dioxide, waste products, and body heat that must be managed. These biological requirements cannot be reduced through engineering. They emerge from physics and chemistry, operating at cellular scales. Multiply these requirements by population size. A minimum viable population for multi-generational voyages might number in the thousands or tens of thousands to maintain genetic diversity and prevent inbreeding depression. Each person requires food, water, air, and living space for their entire lifetime. The generation born mid-voyage requires the same resources as the generation that departed Earth. Multiply again by voyage duration. A 425-year journey to Alpha Centauri spans roughly 17 human generations. Each generation consumes resources for roughly 25 years before producing the next generation. The total resource requirements equal the per-person requirements multiplied by population size, multiplied by voyage duration. The numbers grow large quickly. Closed-loop life support attempts to solve this through recycling. Instead of carrying all food, water, and oxygen for the entire journey, process waste products back into usable resources. Plants convert carbon dioxide to oxygen while producing food. Water treatment systems purify wastewater for reuse. Composting transforms biological waste into fertilizer. In principle, a sufficiently large biosphere could sustain itself indefinitely. Current closed-loop systems fall dramatically short of this ideal. The International Space Station recycles approximately 90% of water, but requires regular resupply of food, oxygen, and other consumables from Earth. Biosphere 2. The largest closed ecological system ever built on Earth, failed to maintain stable atmospheric composition and required external intervention within 2 years. No fully closed life support system has ever operated successfully for even a decade. The efficiency requirement becomes clear through mathematics. If a life support system recycles 99% of resources and loses 1% per cycle, the losses compound over time. After 100 cycles, cumulative losses reach approximately 63%. After 500 cycles, losses approach 99%. A journey spanning 400 years with daily or weekly cycling would exhaust even the most efficient systems without massive initial reserves. Initial reserves add mass that grows exponentially with voyage duration. If 10% efficiency losses accumulate over the journey, you must carry 10% more initial resources. If 50% losses accumulate, you must carry 50% more. If losses potentially approach 100%, you must carry backup reserves approaching complete redundancy. The mass required for life support scales with mission duration through relationships that become exponential as losses compound. Redundancy requirements compound this further. Generation ships cannot call for help. If the oxygen generation system fails, passengers die within minutes. If water recycling fails, they die within days. If food production fails, they die within weeks. Every critical system requires backups capable of sustaining the population while repairs occur. Multiple redundancy levels mean multiple copies of systems that already mass thousands of tons. Structural mass for containing a pressurized biosphere adds another exponential factor. The habitable volume must contain atmosphere at comfortable pressure against the vacuum of space. Larger populations require larger habitats. Larger habitats require thicker walls or stronger materials to contain internal pressure. The structural mass scales faster than linearly with interior volume, because surface area grows with the square of dimension, while volume grows with the cube. This brings us back to the real limitation that generation ships cannot escape. The mass required for multi-century life support grows through compounding factors, with voyage duration, population size, recycling efficiency, and redundancy requirements. Longer journeys to more distant stars require larger populations for genetic viability over more generations. Larger populations require more life support mass. The exponential mathematics operates on different variables than the rocket equation, but produces similarly impossible numbers for ambitious missions. A generation ship to Alpha Centauri might mass millions of tons with minimal population and optimistic life support assumptions. A generation ship to stars 10 or 20 light-years distant would require correspondingly larger populations for journeys spanning millennia. The masses escalate toward billions of tons. Construction and launch of such vessels faces the original rocket equation problem with vengeance. Generation ships do not escape exponential constraints. They transform propellant mass exponentials into life support mass exponentials. Alcubierre warp drives appear to offer genuine escape from all subluminal constraints. Mexican physicist Miguel Alcubierre published a remarkable paper in 1994 describing a space-time configuration that would permit faster-than-light travel without violating Einstein's special relativity. The concept captured public imagination as science finally validating science fiction's warp drives. Alcubierre's solution exploits a subtlety in relativity. Einstein's equations prohibit matter or information from traveling through space faster than light, but the equations place no limit on how fast space itself can expand or contract. During cosmic inflation, the universe expanded faster than light, without violating relativity because the speed limit applies to motion through space, not to the motion of space itself. The Alcubierre metric creates a bubble of flat space-time, surrounded by a region where space contracts ahead of the bubble and expands behind it. A spacecraft inside the bubble remains stationary relative to local space. The bubble itself moves through external space-time at arbitrary velocity. Passengers experience no acceleration because they are not moving through space. Space carries them along like a surfer riding a wave. The mathematics appears to permit unlimited speeds. A warp bubble could theoretically travel at any multiple of light speed. Alpha Centauri becomes reachable in days rather than years or centuries. The observable universe becomes accessible within human lifetimes. All previous limitations discussed in this script seem to evaporate, but Alcubierre's solution requires exotic matter with negative energy density. Normal matter has positive energy density. Empty space has zero or slightly positive energy density. Negative energy density would create repulsive gravity, pushing space-time apart rather than pulling it together. This property is essential for maintaining the warp bubble geometry. Without negative energy matter, the mathematics collapses. No confirmed observation has ever detected matter with negative energy density. Quantum field theory permits certain configurations called squeezed vacuum states to exhibit small negative energy densities in limited regions, but these cannot be sustained or accumulated. The Casimir effect produces tiny negative energy densities between closely spaced plates, but the amounts are infinitesimal compared to warp drive requirements. Alcubierre's original calculations estimated the energy requirement for a human-scale warp bubble. The quantity of negative energy matter needed exceeded the mass energy of the observable universe. Subsequent refinements by physicists including Harold White reduced estimated requirements by many orders of magnitude through geometric optimizations. The most optimistic calculations still require negative energy, equivalent to the mass of Jupiter concentrated into a thin shell around the spacecraft. Jupiter's mass energy equivalent, calculated using Einstein's equation, equals approximately 1.8 times 10 to the 47th joules. This exceeds total human energy consumption throughout history by factors of billions. Even if negative energy matter existed and could be produced, accumulating Jupiter masses of the stuff lies beyond any conceivable industrial capability. The engineering requirements make antimatter production look trivially easy by comparison. The exotic matter problem reveals a deeper issue about theoretical physics. General relativity is a mathematical framework describing how matter and energy curve space-time. The equations permit many configurations that may not correspond to physical reality. Warp drives belong to a category physicists call solutions of general relativity that probably cannot exist. The equations allow them. Quantum mechanics and thermodynamics likely forbid them. The same mathematical framework permits time machines, naked singularities, and infinite energy extraction from rotating black holes. None of these have ever been observed. The universe appears to enforce constraints beyond those explicit in Einstein's equations. Wormholes face identical exotic matter requirements. These tunnels through space-time could connect distant points, potentially allowing instantaneous travel across any distance. Science fiction portrays wormholes as shortcuts through the cosmos, bypassing the vast emptiness between stars. The mathematics of general relativity does permit wormhole solutions. Maintaining a traversable wormhole requires threading exotic matter through its throat. Without negative energy density material holding the throat open, the wormhole collapses faster than anything could pass through. The amounts required, again, approach planetary or stellar mass energy equivalents. The same objections that doom warp drives apply equally to wormholes. Even if exotic matter existed and warp drives or wormholes could be constructed, both technologies face causality paradoxes. Faster-than-light travel, combined with special relativity, permits time travel into the past. Different observers moving at different velocities would disagree about the temporal ordering of events connected by faster-than-light signals. Some observers would see effects preceding their causes. Time travel creates logical contradictions that many physicists believe nature must forbid. The grandfather paradox, where a time traveler prevents their own birth, represents the most famous example. Either the universe prevents such paradoxes through unknown mechanisms, or our understanding of physics contains fundamental errors. Most physicists bet on prevention rather than paradox. Stephen Hawking proposed the chronology protection conjecture, suggesting that unknown physical principles prevent the creation of time machines. The mathematics of general relativity permits closed time-like curves, but quantum effects or other mechanisms may intervene whenever conditions approach time machine formation. If this conjecture holds, it applies equally to warp drives and wormholes, because both would enable causality violations if functional. All proposed theoretical escapes from conventional propulsion constraints fail upon examination through independent mechanisms. Antimatter exists, but cannot be produced in useful quantities through any foreseeable technology. Current production rates would require billions of years to accumulate meaningful amounts. Storage requirements exceed demonstrated capabilities by factors of millions. Energy economics make antimatter merely an inefficient storage medium rather than a power source. Beam propulsion eliminates onboard fuel but transfers mass requirements to infrastructure that faces its own scaling limits. Lasers powerful enough to accelerate human payloads would require arrays larger than nations. Sail materials with necessary properties may not be physically achievable. Deceleration at destinations remains unsolved, without pre-positioned infrastructure that faces the original propulsion problem. Generation ships accept slow travel but face exponential growth in life support mass. Recycling efficiency limits compound losses over long voyages. Redundancy requirements multiply system masses. Structural constraints for pressurized habitats scale unfavorably. Population requirements for genetic viability increase mass demands for longer journeys. Exotic physics escapes require materials that probably do not exist. Negative energy density matter has never been observed in quantities useful for propulsion. Mathematical solutions of general relativity may not correspond to physically instantiable configurations. Causality protection may fundamentally forbid faster-than-light travel, regardless of the mechanism proposed. The universe appears to forbid interstellar travel through multiple independent mechanisms. Each attempted escape route encounters its own barrier. The barriers arise from different physics, different engineering constraints, different mathematical limits, yet they converge on the same conclusion. Stars remain unreachable for biological beings regardless of which propulsion concept is pursued. This convergence of constraints suggests something profound about cosmic organization. The limitations are not accidental or arbitrary. They emerge from fundamental physics operating across multiple domains. Conservation of momentum creates the rocket equation. Thermodynamics limits energy density. Material science constrains structural possibilities. Quantum mechanics may forbid exotic matter. Each domain contributes its own barrier. The next chapter examines what these combined constraints mean for humanity's cosmic future. The ceiling exists. The ceiling appears permanent under known physics. What lies within reach, despite these limits? What does the existence of such limits imply about other intelligent species throughout the universe? The mathematics that imprisons humanity may imprison every technological civilization that ever arises. The mathematics converges on a sobering conclusion that no amount of technological optimism can overturn. Human travel through space faces an absolute limit imposed by exponential mass growth. This limit is not arbitrary. It is not a failure of imagination or engineering. It emerges from the fundamental relationship between momentum, energy, and mass that governs all motion through the universe. No civilization, however ancient or advanced, can violate conservation laws without violating reality itself. 3 chapters of analysis have demonstrated this truth from multiple angles. Chemical rockets confront the exponential wall within the inner solar system. Ion engines and nuclear rockets push the wall outward, but cannot eliminate it. Antimatter propulsion, the theoretical maximum of energy density, still faces exponential constraints at stellar distances. Beam propulsion transfers the problem from spacecraft to infrastructure without solving it. Generation ships transform propellant mass requirements into life support mass requirements while maintaining exponential growth. Exotic physics escapes require materials that probably do not exist in any physically realizable universe. Each proposed solution fails independently. Together, they reveal a pattern that suggests cosmic design rather than cosmic accident. The universe has constructed multiple overlapping barriers, preventing rapid interstellar travel. Breach one barrier, and another stands behind it. The convergence implies that the limitation is fundamental rather than incidental. Physics does not merely make interstellar travel difficult. Physics makes interstellar travel nearly impossible for any conceivable technology operating within known laws. Defining the absolute ceiling requires specifying what propulsion technology could theoretically achieve. Consider the maximum case that physics permits. Matter-antimatter annihilation converts rest mass entirely to energy. The exhaust products travel at substantial fractions of light speed. No chemical or nuclear process achieves higher energy density. Antimatter represents the ceiling of what rockets can theoretically burn. Even with perfect antimatter propulsion, mass ratios grow exponentially with velocity requirements. The rocket equation applies regardless of fuel type. Higher exhaust velocities reduce the exponent, but do not eliminate it. Calculate what antimatter permits. Assume an effective exhaust velocity of 30% of light speed, representing optimized antimatter rocket performance. Reaching 50% of light speed with deceleration capability requires a delta V of approximately 300,000 kilometers per second. The equation demands a mass ratio exceeding 150. 400 seems manageable after the billions and trillions demanded by lesser propulsion systems. A spacecraft 99.75% propellant by mass, with only 1/4% for structure and payload. Challenging, but not physically impossible. Antimatter appears to open a door that other technologies keep closed, but examine what this mass ratio actually requires. If the final spacecraft after all propellant is expended masses 100 tons, including structure and payload, the initial fueled mass must exceed 40,000 tons. Half of that mass, 20,000 tons, would be antimatter. The other 20,000 tons would be ordinary matter for the antimatter to annihilate against, plus containment systems, engines, structure, and payload. 20,000 tons of antimatter exceeds global production capacity by factors of billions of trillions. Current annual production measured in nanograms would require timescales exceeding the age of the universe to accumulate such quantities. The mass ratio is mathematically feasible. The fuel supply is physically impossible. The exponential barrier transforms from mass ratios to production rates, maintaining its stranglehold through different variables. Increased velocity requirements and even theoretical antimatter rockets collapse into impossibility. Reaching 90% of light speed demands mass ratios exceeding millions. The exponential curve climbs toward infinity regardless of starting point. No fuel achieves infinite energy density. No engine achieves light speed exhaust velocity. The mathematics guarantees that some velocity threshold exists, beyond which mass ratios exceed constructible limits for any propulsion technology that physics permits. The practical ceiling for human travel likely lies somewhere between 1 and 10% of light speed. Below 1%, journey times to nearby stars exceed human lifespans by factors that make the missions meaningless for living passengers. Above 10%, mass ratios for round-trip missions become prohibitively large, even with propulsion systems beyond current technology. This velocity envelope defines what biology and physics together permit. Consider what these velocities mean for reaching specific destinations. At 5% of light speed, approximately 15,000 kilometers per second, Alpha Centauri lies 85 years away. Barnard's star at 6 light-years requires 120 years. Wolf 359 at approximately 8 light-years needs 160 years. Lalande, 21,185 at roughly 8 light-years takes similar time. Sirius at 9 light-years requires 180 years. Tau Ceti at approximately 12 light-years needs 240 years. These journey times exceed human lifespans but might accommodate suspended animation technology or generation ships accepting multi-century voyages. The destinations remain theoretically reachable, even if practically challenging. Passengers departing Earth might have great-great-grandchildren arriving at Alpha Centauri. Frozen colonists might wake after a century to find themselves orbiting an alien star. The timescales are daunting but not physically impossible. Beyond roughly 20 light-years, even optimistic velocities produce journey times exceeding what biological humans could endure through any foreseeable technology. At 5% of light speed, a star 20 light-years distant requires 400 years of travel. Passengers would need to survive 4 centuries of cosmic radiation, mechanical degradation, psychological isolation, and life support system operation. No credible engineering extends reliability that far. No biological intervention extends human lifespan that far. The practical limit for human passengers terminates around 15 to 20 light-years from Earth. The solar neighborhood within this radius contains approximately 120 to 150 star systems, depending on exactly where the boundary is drawn. Many of these systems host confirmed exoplanets. The TRAPPIST-1 system at 40 light-years contains 7 rocky planets, 3 in the habitable zone where liquid water could exist. Proxima Centauri hosts a roughly Earth-mass planet in its habitable zone. Tau Ceti may harbour multiple planets, including potential habitable zone candidates. This stellar neighbourhood represents humanity's realistic exploration envelope under any foreseeable technology. A tiny bubble surrounding our Sun containing perhaps 150 stars out of the Milky Way's 400 billion. The ratio between accessible stars and total galactic stars equals approximately 1 in 3 billion. Humanity's reach extends to 1/3 billionth of our home galaxy before the exponential wall becomes insurmountable. The Milky Way galaxy spans roughly 100,000 light-years from edge to edge. Our Sun orbits approximately 26,000 light-years from the galactic center. At 5% of light speed, crossing from our location to the galactic center would require roughly 520,000 years. Reaching the far edge of the galaxy would take approximately 1.5 million years. Crossing the entire galactic disk requires 2 million years of continuous travel. 2 million years ago, the genus Homo was just emerging in Africa. Australopithecus still walked the savannah. Human ancestors had not yet mastered fire. The timescales required for galactic traversal exceed the entire duration of human evolution. No plausible continuity of purpose, culture, or technology extends across such intervals. Galactic exploration through physical travel remains permanently impossible for biological beings, regardless of propulsion technology. The Andromeda Galaxy, our nearest large galactic neighbour, lies approximately 2.5 million light-years distant. At 5% of light speed, reaching Andromeda would require 50 million years of travel. 50 million years ago, dinosaurs had been extinct for 15 million years. Early primates were just beginning to diversify. The geological and biological changes across such timescales exceed comprehension. No mission architecture could maintain coherence across 50 million years. The observable universe extends approximately 46 billion light-years in every direction from Earth. This radius represents the maximum distance from which light has had time to reach us since the Big Bang. At 5% of light speed, traversing the observable universe would require roughly 920 billion years. The universe itself is only 13.8 billion years old. The timescale for cosmic traversal exceeds the age of existence by factors of nearly 70. These numbers establish the ceiling with mathematical certainty. Humanity will never explore more than an infinitesimal fraction of cosmic space. The galaxy remains forever beyond reach. Other galaxies represent pure abstraction for biological beings. The observable universe exists as a vista for telescopes and mathematics rather than a destination for travelers. Physical presence will forever remain confined to our immediate stellar neighborhood. Robotic probes face similar but slightly extended limits compared to human passengers. Without life support requirements, probe masses can remain dramatically smaller. A kilogram-scale probe requires far less propellant than a 1,000-ton crewed spacecraft. Without biological timescales constraining journey duration, probes can accept voyages lasting millennia rather than centuries. A probe traveling at 1% of light speed might reach stars 100 light-years distant in 10,000 years, eventually transmitting data back to Earth or its successor civilizations. But probe capability scales with mass. More capable instruments require more mass. Higher resolution cameras need larger optics. More sensitive detectors need more shielding. Longer range transmitters need larger antennas and more power. Better computers need more processing substrate. Each capability improvement adds mass that the propulsion system must accelerate. More mass requires more propellant. The rocket equation applies to robotic probes exactly as it applies to crewed vessels. Higher velocities require exponentially more propellant for a given payload mass. The exponential relationship does not distinguish between human passengers and silicon instruments. Mass is mass. Momentum is momentum. Conservation laws operate identically on all matter. Breakthrough Starshot proposes gram-scale probes precisely because the exponential constraints become manageable only at extremely low masses. A 4-gram probe accelerated by external lasers might reach 20% of light speed. But 4 grams accommodates only the most primitive instruments. A camera chip, a basic processor, a tiny transmitter, a thin sail. Such probes can return images and simple data. They cannot conduct sophisticated science, establish communication relays, or prepare for future missions. Scaling probe mass toward useful scientific capability reintroduces exponential constraints. A probe carrying a mass spectrometer for analyzing planetary atmospheres might mass hundreds of kilograms. A probe carrying sample return capability might mass thousands of kilograms. Each mass increase multiplies propellant requirements through the same exponential relationship that dooms crewed missions. The probe version of the ceiling sits somewhat higher than the human version. Robotic explorers might eventually reach stars 50 or 100 light-years distant through patient programs spanning millennia. But the same exponential mathematics that confines humans to the local stellar neighborhood confines robots to the local galactic neighborhood. The barrier is fundamental to physics, not to biology. This brings us back to the real limitation one final time, stated with absolute clarity. The rocket equation demands exponential fuel mass growth for linear velocity gains. This relationship derives from conservation of momentum, one of the most fundamental principles in physics. Every rocket that accelerates does so by expelling mass. The momentum gained by the rocket equals the momentum carried away by the exhaust. No engineering can change this relationship. No technology can violate conservation laws. The mathematics is not engineering pessimism dressed in equations. It is physical truth expressed through mathematics. The universe built this constraint into the fabric of space-time when it established how momentum and energy relate to mass and velocity. The constraint existed before life evolved. It will exist after all stars have burned out. It applies uniformly throughout the cosmos to any material object attempting to change its velocity through reaction propulsion. The cosmic quarantine extends to every intelligent species that might exist elsewhere in the universe. Any civilization using rockets faces the same equation. Any civilization wanting to travel fast confronts the same exponential barrier. The laws of physics apply uniformly throughout the observable universe. What constrains humanity constrains every technological species that has ever arisen or ever will arise on any world orbiting any star in any galaxy. This perspective illuminates the Fermi paradox from an angle rarely considered. In 1950, physicist Enrico Fermi asked a question that has haunted astronomy ever since. Given the age of the galaxy, roughly 13 billion years, and the number of stars it contains, roughly 400 billion, and the apparent ubiquity of planets, why do we see no evidence of extraterrestrial visitors? If intelligent life arises with any regularity, civilizations millions of years older than humanity should have colonized the entire galaxy by now. Where is everybody? Proposed answers span every conceivable possibility. Perhaps intelligence is far rarer than optimists assume. Perhaps civilizations destroy themselves through nuclear war or environmental collapse before achieving interstellar capability. Perhaps advanced beings transcend physical existence, losing interest in exploration. Perhaps they deliberately hide from primitive species like humanity. Perhaps we are truly alone in a cosmos that produced awareness exactly once. Exponential mass growth offers a simpler explanation that requires no special assumptions about the nature or behavior of intelligence. Perhaps alien civilizations exist in abundance throughout the galaxy. Perhaps thousands or millions of species have achieved technological sophistication far exceeding humanity's current level. Perhaps they have fusion reactors and antimatter factories and engineering capabilities beyond our imagination. None of them can cross interstellar distances rapidly because physics forbids it. Every species confronts the same rocket equation. Every species faces the same exponential barrier. Every species finds that chemical rockets enable solar system exploration, while interstellar travel demands propulsion systems they cannot build. The mathematics operates identically on all matter, regardless of who assembled it. Imagine what such trapped civilizations might look like. Picture a species that evolved 3 billion years before Earth formed, around a star in the galactic core. They developed spaceflight, colonized their solar system, and built a thriving interplanetary civilization. They detected radio signals from neighboring stars and knew other intelligences existed. They dreamed of contact. They calculated what reaching those neighbors would require. The mathematics defeated them, as it defeats everyone. Their best propulsion systems, perhaps nuclear pulse or fusion drives, could achieve a few % of light speed at costs that strained their entire civilization. The nearest inhabited star system lay 15 light-years away. A one-way voyage would take 3 centuries. A round trip exceeds any reasonable planning horizon. Communication by radio required 30 years for each exchange. They could confirm intelligence existed nearby. They could never meet it. 3 billion years later, that civilization still inhabits its home system. Perhaps they sent probes that arrived centuries ago at neighboring stars, transmitting data that returned centuries after that. Perhaps they received probes from neighbors who made the same calculations and reached the same conclusions. But no ships carry passengers between systems. No trade routes connect stellar civilizations. Each species develops alone, aware of others, unable to interact meaningfully across the void. The galaxy might contain millions of such civilizations, separated by physics rather than by choice. Each intelligence develops within its stellar system. Some spread to nearby stars through patient efforts spanning millennia. None achieves galactic presence because exponential mass growth prevents rapid expansion across the tens of thousands of light years, separating stellar neighborhoods. Consider what galactic colonization would actually require. A civilization wanting to spread across the galaxy must accelerate colony ships to substantial fractions of light speed, deliver viable populations to target systems, establish self-sustaining colonies capable of launching their own expeditions, then repeat the process across thousands of generations spanning millions of years. Each step faces the exponential constraint. Each link in the colonization chain requires propulsion technology that fights the rocket equation. Even if individual interstellar crossings were possible at enormous cost, the repetition required for galactic colonization multiplies impossibility by impossibility. Colonizing one nearby star system demands civilization-scale resources. Colonizing 10 demands those resources repeated 10 times. Colonizing the galaxy's 400 billion stars demands repetition beyond any meaningful calculation. The exponential mathematics compounds across both individual missions and total colonial scope. The silence we observe in the cosmic radio spectrum may reflect not absence but imprisonment. Alien civilizations are not visiting Earth because they cannot visit Earth. They are not colonizing the galaxy because they cannot colonize the galaxy. They sit in their own stellar neighborhoods, perhaps detecting our radio transmissions, perhaps wondering why we have not visited them, perhaps working on their own futile schemes to defeat the rocket equation. This interpretation transforms human cosmic isolation from tragedy to normalcy. The universe distributes intelligence across countless worlds, while preventing that intelligence from mixing across interstellar distances. Cosmic civilization remains forever local. The implications extend beyond exploration into fundamental questions about the purpose of intelligence in the universe. If conscious beings cannot spread freely through space, what role does consciousness play in cosmic evolution? Why would the universe produce awareness if that awareness remains permanently confined to isolated neighborhoods? Perhaps consciousness serves functions that do not require spatial expansion. Perhaps the purpose of intelligence is to observe and comprehend, rather than to colonize and control. Humanity has spent centuries developing scientific instruments that extend perception far beyond biological limits. Telescopes reveal galaxies billions of light-years distant. Radio receivers detect signals from the universe's earliest epochs. Gravitational wave observatories sense black hole collisions across cosmic distances. We can study the universe in exquisite detail without physically traveling through it. Knowledge accumulates through observation. Understanding deepens through analysis. The cosmos becomes comprehensible to minds that remain fixed in place. Physical confinement does not prevent intellectual expansion. Perhaps this represents the actual cosmic role of intelligence. Observers who understand rather than explorers who occupy. The universe may prefer distributed awareness over centralized empires. Exponential mass scaling ensures this distribution by preventing any single intelligence from dominating cosmic space. Every species develops its own understanding shaped by its particular stellar environment. Every consciousness contributes unique perspectives that would be homogenized if galactic expansion were possible. The ceiling preserves diversity by preventing convergence. Alternatively, the ceiling may function as a filter testing civilizations for wisdom rather than capability. Species that accept physical limits and develop sustainably within their stellar neighborhoods might persist indefinitely. Species that exhaust resources, attempting impossible expansion, might collapse and vanish. The rocket equation selects for maturity over ambition, teaching intelligence to live within mathematical constraints rather than destroying itself fighting them. Civilizations surviving this filter would recognize the exponential barrier as a boundary rather than a challenge. They would focus development on their solar systems rather than dreaming of galactic conquest. They would achieve equilibrium with available resources rather than pursuing infinite growth. They would find meaning in understanding rather than expansion. Humanity has not yet passed this test. Our culture celebrates boundary breaking and limitless ambition. Our economic systems require perpetual growth. Our narratives glorify conquest and expansion. We have not internalized the lesson that some limits are fundamental rather than temporary. The rocket equation offers that lesson with mathematical clarity. Whether we learn it through wisdom or through collapse remains to be determined. The immediate future remains bright despite ultimate limits. Human presence in the solar system will likely expand dramatically over coming centuries. Current technology already enables lunar bases and Mars settlements. Nuclear thermal rockets could open the outer planets to human exploration. The asteroid belt contains mineral wealth exceeding all reserves on Earth. Jupiter's moons harbor oceans that might support life. This represents an enormous expansion of human presence, even within the constraints physics imposes. The solar system spans roughly 80 astronomical units, from the Sun to the Kuiper Belt's outer edge. An astronomical unit equals Earth's orbital radius, approximately 150 million kilometers. 80 astronomical units means 12 billion kilometers of accessible space containing billions of tons of accessible resources. Chemical and nuclear rockets suffice for exploring this domain. Delta-V requirements for reaching any point in the solar system remain within the difficult but achievable range. Mass ratios climb toward tens or hundreds, but not toward billions or trillions. The exponential wall stands beyond Pluto, beyond the Oort cloud, somewhere in the void between our Sun and Alpha Centauri. Everything sunward of that wall lies within reach. Mars offers an entire planet for potential colonization. Its surface area equals Earth's land area. Its resources include water ice, atmospheric carbon dioxide for fuel synthesis, and mineral deposits unexplored by human hands. Terraforming remains speculative, but self-sustaining settlements appear achievable within centuries. Millions of humans might eventually call Mars home. The asteroids offer resources that dwarf terrestrial deposits. A single metallic asteroid 1 kilometer across contains more platinum group metals than humanity has ever mined. Thousands of such asteroids populate the belt between Mars and Jupiter. Mining technology remains undeveloped but physically straightforward. The wealth available in the asteroid belt could support human civilization for millions of years without exhausting supply. Jupiter's moon Europa conceals an ocean beneath its icy crust. Tidal heating from Jupiter maintains liquid water, despite surface temperatures far below freezing. The ocean might contain more water than all Earth's oceans combined. Whether life exists, there remains unknown. Exploring Europa represents one of the most profound scientific opportunities within human reach. Saturn's moon Enceladus offers similar possibilities in a smaller package. Geysers of water vapor erupt from cracks in its icy surface, spraying material into space that Cassini spacecraft analyzed directly. The eruptions confirm a subsurface ocean exists. Organic molecules detected in the plumes suggest chemistry that might support life. Enceladus may be the most accessible location in the solar system for finding extraterrestrial biology. Saturn's moon Titan offers a world stranger than Mars. Dense nitrogen atmosphere supports methane weather systems, including rain, rivers, and lakes. Complex organic chemistry produces hydrocarbon deposits that might serve as fuel or feedstock. The environment differs radically from Earth, but supports physical phenomena familiar from terrestrial experience. Titan could host human presence in pressure suits rather than spacesuits. Neptune's moon Triton likely originated as a Kuiper Belt object captured by Neptune's gravity. Its retrograde orbit and unusual geology suggest violent origins. Geysers of nitrogen gas indicate internal heat sources that remain mysterious. Triton represents the frontier of accessible exploration, a stepping stone toward the outer solar system's countless small bodies. The Kuiper Belt itself contains thousands of objects larger than 100 kilometers in diameter and millions of smaller bodies. These frozen remnants of solar system formation preserve pristine material from the solar nebula. Scientific value aside, the Kuiper Belt resources could support expansion far beyond the inner planets. Water ice, frozen gases, and rocky materials exist in quantities sufficient for any conceivable human need. All of these destinations lie within reach of propulsion technology that humans have already demonstrated. The barrier is not physics but economics and priorities. Expanding human presence through the solar system requires investment that competing demands have prevented. But nothing in the rocket equation prevents solar system development. The exponential wall stands beyond, not within, our stellar neighborhood. Beyond the solar system, outposts around nearby stars remain theoretically possible, though enormously challenging. Generation ships carrying self-sustaining populations might reach Alpha Centauri after centuries of flight. Suspended animation technology might preserve colonists through interstellar crossings that living passengers could not consciously endure. Robotic probes might prepare target systems for eventual human arrival. Each destination beyond the Sun would develop largely independently of Earth and each other. Communication delays measured in years or decades would prevent real-time coordination. Colonies would evolve their own cultures, technologies, and perhaps eventually their own species as isolation enables genetic drift. Interstellar humanity would fragment into countless branches no longer recognizable as a single civilization. This fragmentation represents the natural consequence of exponential mass constraints. The same physics, preventing rapid travel, prevents the coordination needed for unified galactic presence. Interstellar colonies would not constitute an empire, or even a federation. They would represent independent experiments in human existence, aware of each other through light-speed signals but incapable of meaningful interaction. Perhaps this represents an acceptable future. Independent human lineages developing diverse solutions to the challenges of existence. Cultures separated by centuries of travel time, evolving in directions no central authority could predict or control. Unity sacrificed for survival and diversification, but the solar neighborhood represents the horizon, regardless of how human presence develops within it. The galaxy beyond our immediate vicinity will forever remain unexplored by human beings or human machines. The universe beyond our galaxy represents pure abstraction for all biological intelligence. We can photograph Andromeda. We can measure its spectrum. We can calculate its mass and motion. We will never set foot on any world, orbiting any star within its spiral arms. This conclusion requires no pessimistic assumptions. It requires no failure of human creativity or ambition. It emerges directly from conservation of momentum through the rocket equation's exponential mathematics. The universe permits local existence while forbidding cosmic presence. The same laws that allowed stars to form and planets to coalesce, and life to evolve also confine that life to its birthplace. Tsiolkovsky understood this a century ago, even as he dreamed of humanity spreading through space. He wrote that Earth is the cradle of humanity, but one cannot live in a cradle forever. His equation enabled the rockets that carried humans beyond the cradle to the moon. That same equation confines humanity to the nursery surrounding the cradle. We can explore the nearby rooms. We cannot leave the house. The ceiling is real. The ceiling is permanent under known physics. The ceiling is acceptable to civilizations mature enough to recognize limits as boundaries for wisdom rather than obstacles to ambition. Within its constraints lie wonders enough for any species across any time span. The solar system beckons with resources and mysteries that will challenge humanity for millions of years. The nearby stars offer horizons that might be reached through efforts spanning civilizations. Beyond lies the universe we can see but never touch. Galaxies by the trillions stretching toward horizons 13 billion years in the past. Stars beyond counting, harboring worlds beyond imagining. Cosmic structures spanning scales that dwarf human comprehension, all of it visible through telescopes. None of it accessible through rockets, forever calling, forever unreachable. Exponential mass scaling creates this ceiling through mathematical inevitability. Every improvement in propulsion efficiency delays, but does not eliminate the exponential growth that eventually overwhelms any mission. Every theoretical escape route encounters its own impossible requirements, rooted in different physics that converge on the same conclusion. The universe that permitted our existence also confines our existence. Stars forged the heavy elements in our bodies through nuclear fusion. Supernovae scattered those elements through space to form planets. Chemistry on one of those planets produced life that eventually developed awareness. The physics enabling this cosmic biography is the same physics imprisoning its subjects within their stellar nurseries. We are fortunate beyond measure to exist at all. The probability that any particular arrangement of atoms would achieve consciousness approaches zero. Yet here we are, contemplating our cosmic situation. Gratitude for existence need not require infinite reach. The cosmos gave us life, awareness, understanding, and a stellar neighborhood to explore. The cosmos did not give us the galaxy. The cosmos did not give us the universe. Perhaps the cosmos gave us enough. This is the absolute limit of human travel through space. Embrace it not with despair but with focus on what lies within reach. Explore everything within its bounds, knowing that the bounds themselves teach lessons about the nature of existence. The rocket equation launched humanity beyond Earth. The rocket equation confines humanity near Earth. Both truths emerge from the same mathematics. Both reflect the same conservation laws. The universe is not cruel in imposing limits. The universe simply is what it is. Physics does not negotiate. Physics does not make exceptions. Physics tells us what reality permits and what reality forbids. Every rocket that ever launches will obey Tsiolkovsky's equation. Every mission that ever flies will confront exponential mass growth. Every dream of stellar empire will eventually shatter against the mathematical wall. This is not pessimism about human potential. This is physics describing cosmic architecture. Human wisdom lies in hearing what physics says and accepting what it means. The stars will remain destinations for light and radio waves rather than for spacecraft and passengers. Telescopes will continue revealing cosmic wonders across billions of light years. Transmitters will continue sending human messages towards stars we can never visit. Knowledge will expand even as physical presence remains confined. Understanding will deepen even as ambition encounters limits. The ceiling exists. The ceiling teaches. The ceiling defines who we are and what we can become. Within its boundaries lies everything humanity needs to flourish for millions of years. Beyond its boundaries lies everything we must accept we can never possess. The distinction matters not for what it denies, but for what it clarifies. This is the absolute limit of human travel through space. The rocket equation defines that limit through exponential mathematics that no technology can escape. The limit lies within the local stellar neighborhood, perhaps 20 light-years from Earth for biological travelers, perhaps 100 light-years for robotic probes. Beyond lies infinity that belongs to telescopes and imagination rather than to rockets and travelers. We are star stuff contemplating stars we can never reach. We are cosmic observers confined to cosmic corners. We are intelligence aware of limits that intelligence cannot transcend. In this awareness lies whatever wisdom the universe offers to beings capable of understanding their situation. The cosmos gave us enough. The cosmos gave us existence, awareness, understanding, and a stellar neighborhood to call home. Accept what the cosmos gave. Explore what the cosmos permits. Wonder at what the cosmos reveals. Rest content with limits that define the possible.